Welcome to the second section in the Introduction to 6502 Assembly Programming. In this section, we'll be covering a brief introduction to computer architecture. This is an entire undergraduate course, in electrical or computer engineering degrees, and we're going to cover in like 10 slides, maybe 15. We're not going to cover all the details, obviously. We're actually just going to barely scratch the surface of kind of what you need to know to understand how the code works. How the details of the machine actually executes the code, and some more specifics like interrupts aren't very important for most basic programming in assembly. So we're going to skip those topics and just cover the most important ones. All right. First, ROM, read-only memory. This is a non-volatile storage, which means it remains the content remains after a power down. Usually can only be read and never written to, and normally ROM is used to store the program itself. Now, obviously, this isn't always true, and ROM hardly exists in most modern architectures today. Most modern architectures execute program from RAM that is fetched into a cache and all the silly nonsense. But in the 6502 world, people are going to refer to ROM, and what they're meaning is this non-volatile storage, the memory that gets stored and stays when the system powers off and powers back up. Computers work in binary. We covered this in the last class, but we'll briefly cover it again. A bit is a single binary placeholder. Can be either 0 or 1. 8 bits are put together to form what's called a byte. 4 bits come together to form a nibble, so you have 2 nibbles that form a byte. And the key item to note here is the 6502 is an 8-bit machine, meaning that it does all operations in 8-bit size chunks of data. If something is not 8 bits, like a number that you're using, you're just going to have leading zeros, as many leading zeros as you need, until there's 8 bits. On a 64-bit machine, all math operations are done typically 64 bits at a time, and they store data units, data items 64 bits wide. So we have 2 examples here. One is storing the number 26, and one is storing the number of 256. And those are 1A in hexadecimal, and FF in hexadecimal, respectively. And you can see in the binary for the 26 that we have 3 extra leading bits of zeros that aren't really needed. But the machine is always going to operate on 8 bits at a time, the 6502 is, and so all leading zeros to fill into 8 bits are stored. All right. Next part of a computer we're going to talk about is the RAM, and I think this is intuitive to most users because if you think about writing 6502 assembly, you're probably using a computer quite a lot, and so you know about RAM. RAM is the memory in a device that's volatile. It loses content when it's powered down, typically. Can be read to, or read from, or written to. And normally it's used to store program data. And it's the data that is used by the program while it's running. And at least for the 6502, that is generally the case. So it holds the data used by the program. On the right-hand side, we kind of have a visualization of what RAM might look like. We have a few addresses here. Each byte inside of the RAM has an address, and each address will store 1 byte of data. And so you can see here at address 0, we have the value hex 23. At address 1, we have the hex value 56, and so on and so forth. So it's just a big area of data storage that can be written to. The last component of the architecture that we're going to talk about, at least in this set of slides, we'll talk about some of the more details in future slides, is the ALU, the Arithmetic Logic Unit. This is kind of the core of the CPU. This is the core of the processor. It's what runs the program itself. It reads the instructions and executes them. It does what it says to do. So this is what contains all the logic that makes things work. So here we have an example, and I've drawn this diagram. It's typically used as an indicator of storage, and so I'm using it for the ROM, and it's storing the program memory. And in one of the instructions in the program memory, we have an instruction that says to increment the RAM address 3. So what the ALU will do is when it's time to execute the next instruction, it'll read in this instruction. It'll say, okay, this is an increment instruction and I need to increment a value in RAM. So it'll go off to RAM, read the value at address 3, which is currently a 1. And then it says the instruction is an increment. So it'll go ahead and increment that value by 1. So the ALU is kind of how all of the program runs itself. The program is stored over here in ROM. The RAM holds the data values that it get operated on. And the ALU is the one that does the operations. Next topic we're going to talk about are registers. Registers are kind of special locations, special things inside an ALU or CPU that have special behavior. So RAM is just data. It doesn't do anything special or indicate anything special typically. And typically, if it is used for something special in hardware, it's given the name of register. Unlike RAM, sometimes registers don't have addresses, and this depends which CPU that or which processor that you're using, whether they have addresses or not. But that's not really important. The important thing here is that registers have a specific special behavior. In many cases, not all cases, but in a lot of cases, registers may not even be writable, and the hardware sets them directly. We're going to cover a lot of the registers, or most of the registers, in the 6502 in separate sections, but I'll kind of show you the names of them here. And these registers will completely vary if you move to a different microcontroller or microprocessor. So these are very specific to the 6502, and the register sets are a good portion of what makes each different processor unique and how they operate. So kind of the 6 main ones that we have in the 6502 are the accumulator, which is given the name A, the stack pointer, which is given the name SP, the index registers X and Y, which are given X and Y names, the program counter, which is given the name PC, and the final one is the status register, which is given the name S. Those names are assembler specific, and so they might change, they might vary slightly if you're using different assemblers, but this is kind of the normal nomenclature you'll see for these registers. All right, the assembly process. The assembly process is the means by which you take assembly code over here on the left. This is your human readable program. You know, when you write a program, you're writing assembly. And you have to turn that into the code that the machine knows how to operate on. The machine is not reading, you know, the typed out instructions. It's reading what's called machine code. And that's taking the typed assembly and converting it into a set of binary information that it can understand. Tool in the middle that does that is called the assembler. So the assembler takes assembly code and converts it to machine code. And very brief, we'll kind of look at what this looks like. So this will become more important specifically if you're doing something like ROM hacking, where you need to understand the actual machine code. You're looking at the binary data of the output of the assembler. So being able to understand how assembly translates to machine code and taking machine code and disassembling it back to assembly can be important, both operations. We're not going to go into details specifically in this section, but we may cover that a little bit later. So here we have our same example from before, our increment instruction of address 3. And on the left here, we have the assembly version of that. And like we said before, the machine isn't actually going to read in this. We're going to run this assembly code through the assembler, and it's going to produce the machine code that the 6502 reads. And what the 6502 read will look something like this on the left. First, we have an operational code, often called an opcode. And it's a byte that tells the machine what instruction is being run. So in this case, this increment is EE, and I'm not 100% sure that's right. I probably looked it up. I might have got the wrong increment. But anyway, that doesn't matter. The point being is there's a code that indicates what instruction is being run. In this case, it's an increment of a RAM location. Second part of the instruction is going to be the operands, or operand, or maybe none. Some instructions don't have an operand. Some will have multiple operands. But the operands are the data that the instruction is going to execute on. So in this case, this increment instruction is incrementing a RAM address. So the processor needs to know which RAM address to increment. And we wrote address 3 over here. And so the operand on this instruction is address 3. And so the machine code version of increment 3 is EE0003 over here. And likewise, if you were taking a binary file and disassembling it, if you ran into this, you would know that's the corresponding assembly instruction. All right, the last topic we're going to talk about in this section is variables, constants, and literals. And I'll use a little bit of the 6502 nomenclature here, but we'll cover this in a lot more detail in the sections that come where we're covering the actual individual instructions. But understanding these terms and what they mean is important for that fundamental understanding to understand when we get to those sections. So the first is a variable. A variable is a logical entity that has a value that can change. Typically, we're going to think of this in bytes on the 6502, since each RAM address is a byte. But you might have a variable that's a multi-byte variable, so it can store more than a single byte. But it's a logical thing that can be updated. Typically, this is going to be stored in RAM, because RAM is the section CPU that can be updated. So if we go back to that prior example that we saw where the ALU was incrementing an address in RAM, this RAM address over here, the 0003 address, is likely a variable. Maybe it's the number of lives a player has. And so this address in RAM is a variable that represents, the player life count. And they got a 1-up or whatever. And so the game is telling it to increment the number of lives. And so this is our variable here. Constants, just like the word implies, is kind of the opposite of variable. It's a logical entity that has a value that can't change. We'll see in the next slide kind of the difference between constants and literals. Linguistically, they sound very similar, but they're different in programming. So constants are going to be just like the variables, but they're not allowed to change. And depending on the language that you're using, there's different ways to indicate this. In 6502 assembly, there's a couple of mnemonics that are used to store data in the ROM. And this is how you would create a value that can never be changed. So here are a couple examples, and there may be more. I'm pretty sure there are more. But here are two, so you can kind of see this. There's a .byte and a .word. And these two instructions are doing exactly what they say. They are placing specific values into the program memory at whatever address the assembler is currently assembling for. This might not make too much sense right now, but if you had a table of data that might be driving the way one of your characters or enemies behave, you can store that table of data in the program memory, and as that program is running, it can read those values from the table to know, how high the enemy should jump, how fast he can move, how many, projectiles he can shoot, or whatever it is. And so that table is stored in the ROM, and the code, while it's running, can read those values out of that table. And since this is stored in ROM, it can't change. And so those are constants. The last item we'll talk about are literals. And literals are a bit harder to describe without an example. If you look it up, the internet will say it's the raw value that's being used to set a constant or a variable. And without an example, that's kind of hard to conceptualize. So I added a couple of examples here in different languages because the difference in 6502 is a bit more nuanced and a little bit more difficult to understand. So I covered it in more detail in a later section. This is an example from C. And so here we have a loop that we want to do 25 times. We're going to do the same thing 25 times in a row. So we have a variable counter here that's I, and this is a variable, like I just said, because I, every time around the loop, is going to increment by 1. And it's going to do that until it's done it 25 times. The 25 in this example is a literal. This 25 is not stored in a table in constant memory. It's not stored in a RAM address, though at some point during the program execution or the assembly process, it might be stored in either or both. But in the code, it represents a value, a raw value, and the assembler can do what it needs to do with that literal value. Same thing here, we have another example of an if condition. So if the player has 100 coins, give them extra life. So this literal value is 100. In this example, coins is a variable that the literal is being checked against. But there's probably not a value inside of the program memory that has 100 in it. What likely happens for a lot of these literals is that they get turned into operands into an opcode directly. So they don't live in a separate data section in Flash. And that kind of is what differentiates constants in 6502 assembly from literals, is that the literals are most often going to be embedded directly into the code, whereas constants are going to be in a specific location and then addressed like they were data, but just non-changeable data. Well, like I mentioned, we'll see the specifics about how to use literals as we start to get into the more details of the instructions. But like I just said, we haven't covered everything that we need to know yet. But the rest we'll learn in the context of the 6502 assembly and instruction set. It's much better to learn a lot of the concepts when actually seeing them in action, rather than trying to describe the abstractness of them without putting a concrete context around it. So next session, we'll be diving into those registers that we talked about previously and understanding those. Since they're the gut of how the ALU works, it's really important to understand what each of those registers are, what their role is, and how they work, to really understand how each instruction operates in the machine, because almost every instruction is going to use one or more of the registers in each operation, or affect one of the registers in each operation. So understanding them is important. All right, thank you.